As a sound of pain, change, 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 see your word and change love. Oh, how
Morning, everyone. How are we doing? Well, there's nothing to answer, right? I mean, here it is. The question is asking for f prime of 0. And by definition, well, I mean, that second definition of the derivative, right? I mean, normally it's limit as h goes to 0. But we saw that this was equivalent. So this is what you have to evaluate. So evaluate. That's all. That's all the question is asking. For you to take this limit. Of course, being a limit, you're going to evaluate the limit from the left and limit from the right. At what times is the alternative definition preferred? Almost never. Almost never. Here they're using it in the question. So, you just got to adapt. But there it is. Melanie was asking for question 65 on page 183. I don't have the book with me, Melanie. If you have the question, we can discuss it. Somebody was asking about midterm. Difficulty of questions relative to tutorial questions. I think the challenge questions on the tutorial would be good. Why does the other limit not work? It works. Other limit works as well. Other limit definition works as well. But it's a little bit trickier if you use the other definition. It's not as immediate. Jake is asking how to find f of x from the derivative. And in that case, you have to work backwards. As far as this course is concerned, it's not going to be a question we're going to focus on very much. You're just working backwards. So think of it as working backwards. That's all for now. In Calculus 2, Math 141, that's what the entire course focuses on. Anti-differentiation, or the integral. So Melanie is asking, find an equation in the normal line. To the square root of x that is parallel to 2x plus y is equal to 1, or y is minus 2x plus 1. But to answer Jake's question before we tackle this, you're just working backwards. So if they give you the derivative, like x squared plus 1, you ask the question, what function has this as its derivative? And try to work backwards. Just work backwards. Right? I mean, in simple cases, it's relatively easy to do. Yeah. In simple cases, it's relatively easy to do. I will not have office hours today. Today is Monday. I will have office hours tomorrow, though. So we're looking for the normal line to this. If you take the derivative, was there not? Okay, I mean, you see the issue is that there's no actual point that's given. I think that's the issue Melanie was having. If you take the derivative, this is 1 over 2 root x. Right, so I mean, we need to figure out at some point. So the real question is, what is the point? And we don't know what point. So let's call it x equals a. And when x is equal to a, y is equal to root a. And at this point, the derivative is this. So this is the slope of the tangent line. So if this is the slope of the tangent line, the normal line has slope, which is negative reciprocal of this. So negative 2 root a. Hannah, the left-handed limit. Well, let's finish this. We'll come back to that. So slope of the normal line is negative 2 root a. And you know that it's negative 2. So a has to be 1. And then you can finish it up. This would make a good midterm type of question. And people were asking the difficulty with respect to the tutorial questions. And again, I think the challenge questions are good because, you know, oftentimes you have this extra variable coming in. And, you know, even here, very easy, except that you got to know what you're trying to do. So Hannah was saying if you plug in the left-hand limit, so if we just look at the left-handed limit, 0 from the left, first of all, f of 0 is minus 2. For values less than 0, this is the function you're using. So minus 2x plus 5x. F of 0 is minus 2 over x. This is what we're doing. I don't know why you say over 0, but yeah. Well, Pratik, the question was asking, we're looking for a normal line to this, parallel to that. That was the question. The slope is minus 2. People, what's going on there? Well, the final exam schedule is out. You have a link in the link section. Alyssa, either one is going to work here. Either one works, except if you use the other one, you've got an h instead of an x. And the question is asking for the limit as x goes to 0. So you'll have to make a little adjustment, changing x to h. Oh, I see what you mean. Thank you. It's minus 2. So plus 2. Thank you. Absolutely. Absolutely. Thank you. Miriam's asking how we got minus 2 root a is equal to minus 2. Well, again, the question was normal line to this, parallel to that. So we calculated the slope of the tangent line, which is this. And so the slope of the normal line is a negative reciprocal. So negative 2 root a. And the slope of this line is negative 2. So in order for the lines to be parallel, they have to have the same slope. Exactly, Eddie. Very good. All right. Let's move on. Right, last week we were differentiating products and quotients and trig functions. Everything was nice and good. But we're still not able to differentiate something as simple as this. The square root of x squared plus 1. the square root of x squared plus 1, which can be viewed as the composition of two functions, right? The composition of square root of x and x squared plus 1, right? It's made up of these two functions. If we take the composition, f of g, which is f of g of x, right? G of x is x squared plus 1. So everywhere you see an x in your function f, you replace with x squared plus 1, and we get the original function. The original function is a composition of these two simpler functions. These two simpler functions whose derivative you're very well accustomed to. So now the question is, what is the derivative of a composition? And the answer, as people have suggested, comes to us via the chain rule. The chain rule tells you how to differentiate a composition of functions. Let f and g be differentiable. The composition f of g of x is differentiable, and its derivative is f prime of g of x times g prime of x. Before we take an example, let me rewrite this chain rule in another fashion, which is sometimes very useful as well. If we let u be g of x, then f of g of x is really f of u, and d by dx of f of u is d by du of f times du dx, or df du du dx. In other words, df dx is df du du dx. This can be viewed in a terrible abuse of notation. If you think of crossing out the du's, you're left with a df over dx, exactly what you have here. Well, I mean, people are asking what is f of g of x. You have an example right here. So let's first do some exercises. corresponding to this breakup, to this decomposition, the question is asking us to write as a composition of functions and then differentiate. Where y is the square root of x cubed plus 2. So can we realize this as a composition of simpler functions, f and g? The answer is not unique. Is that U substitution? It is not. U substitution is completely different. U substitution has to do with what people were talking about earlier, integrals and antiderivatives. Interestingly enough, though, the U substitution is actually the chain rule in reverse. So that's a nice observation if you've seen that before. All right. So what we want to do now is write y as a composition of simpler functions. And I mean, can we realize that? Can we break this up into a composition of f and g? You tell me. F is square root of x, g is x cubed plus 2. Let's convince ourselves. Suhaira wants me to explain df dx. Well, I mean, you know what that means. It's the derivative of f with respect to x. There's nothing fancy going on here. It's the derivative of f with respect to x. You mean the expression? I don't know what expression you're talking about now. This is just the chain rule rewritten, right? This is f prime of u, so df du, and this is the derivative, du dx. So all I've done here is rewritten the chain rule in a different way. But let's not worry about that for now, and let's concentrate on this. Observe that f of g of x, right? G is x cubed plus 2, and f of x cubed plus 2 is the square root of x cubed plus 2, right? Everywhere you see an x, in f, you're replaced with x cubed plus 2, and that's what you get. So this is now easily seen to be the composition of these two functions. And now, if you apply the chain rule, and let me rewrite the chain rule here. So dy dx of the composition is f prime of g times g prime of x. In other words, you differentiate the outer function, leaving the inner function fixed, times the derivative of the inside. So here, again, if y is the square root of x cubed plus 2, dy dx, right, and this was viewed as the composition of two functions. Y is f of x equal to square root of x, because it works. right? We've just convinced ourselves right here the composition of these two functions is exactly what you wanted. Pamela's asking, how do we know that right off the bat? Well, I mean, with practice you'll see it, right? We're trying to view this as a composition of two simpler functions. So we've realized this function as the composition, and consequently the derivative, according to the chain rule, is f prime of g times g prime of x. But if this is f of x, you know very well what the derivative is, right? You know what the derivative is. The derivative is 1 over 2 root x. And if this is g of x, you know what that derivative is. That's just 3x squared, right? You've decomposed it into simpler functions whose derivatives you're familiar with. So f prime of g of x, here's your f prime, right? This is f prime of g of x was x cubed plus 2. G prime is 3x squared. And f prime of x cubed plus 2, everywhere you see an x in f prime, you replace with x cubed plus 2, and we get 1 over 2 square root of x cubed plus 2 times 3x squared. This is the derivative of that. Let's do a few more of these, decomposing. Eddie is pointing out a nice property, and that's fine. I mean, what I like to think of this as, you know, right? I mean, here we're doing it the long way, we're decomposing. Absolutely, right? It's fine to rewrite this as 3x squared over 2 root. In fact, you should. There it is. Right? I mean, when looking at this, how should you tackle that? And we're going to come to that momentarily. And you're looking at this and you're thinking to yourself, well, I've got the square root of something. I've got the square root of something, so when I differentiate, I'm going to differentiate the square root. You get 1 over 2 square root times the derivative of the inside. That's what the chain rule says. Let's do another one. The long way, by decomposing this as a composition, decompose this into a composition of functions, each of which you know the derivative of. Can the chain rule be applied multiple times, like a function in a function in a function? Absolutely. Absolutely. A nice observation there, thinking ahead. Very nice. Do we have to show our work? Well, again, we're doing this a long way so that people who've never seen the chain rule get accustomed to it, but we're only going to do it for 2 more examples, this one and another one, and we're going to do it immediately afterwards. And Hamza has given us the answer here. F of x is tangent x. And g of x is x squared, right? You see that this is the composition of these two functions, right? G of x is x squared, and everywhere you see an x in your function, f, you replace with x squared. So this is tangent of x squared. Very nice. These two are good functions because you know exactly what their derivatives are. Right? The derivative of tangent is, you saw that last week, you may remember. Derivative of tangent is secant squared. Even if you don't remember, you can take a moment and work it out. Because tangent is sine over cosine. So it's just a quotient rule. The derivative of x squared is 2x. So the derivative of y the derivative of tangent squared, which can be viewed tangent squared, which can be viewed as the composition, by definition, is f prime of g, g prime of x. Right? It's the derivative of this, which is that chain rule. So f prime g of x is x squared times the derivative of g, which is 2x. And everywhere you see an x in f prime, you replace with x squared, and we get secant of x squared times 2x. Secant squared of x squared times 2x. Absolutely. Thank you, Erica. Right? Or, what's the derivative? What do we have here? How would you describe this? To a friend, you would say it's tangent of x squared. It's really a tangent function. You differentiate the tangent, you differentiate the outer function. Derivative of tangent is secant squared. Secant squared of this times the derivative of the inside. Derivative of x squared is 2x. There it is. Let's do one more. Again, we're going to do it the long way, decomposing this as a composition of functions. A composition of two simpler functions, each of which you can differentiate easily. What are they? Does everybody see this? Is this too easy? Questions, perhaps? Take a moment, decompose. What two functions? X to the 1/3, thank you. Cube root of x. And what's the other one? E to the x plus, was it 2? I have plus 1, e to the x plus 1. right? Again, let's convince ourselves, right? I mean, I think everybody has it, but let's convince ourselves by taking the composition again. G of x is proposed to be e to the x plus 1. Everywhere you see everywhere you see an x in your function f, you're replaced with e to the x plus 1. So that's e to the x plus 1 to the 1/3, or cube root of e to the x plus 1. Very good. Very nice. So you see, we're convinced that this y is the composition of these two simpler functions, and you know their derivatives. Derivative of f, 1/3 x to the minus 2/3. Derivative of g, e to the x. So let's put everything together. dy dx, y, which is the composition f of g. So the derivative is f prime of g times g prime of x. G is e to the x plus 1. G prime is e to the x. And everywhere you see an x in f prime, you replace with e to the x plus 1. So this is 1/3 e to the x plus 1 to the minus 2/3 times the e to the x that was outside. We're going to move away from decomposing the function every single time into just reading it off. But you know, if you're having difficulties, you can always come back to this. Pamela is asking, why is f prime equal to this? Well, you know how to take the derivative, right? You know the derivative of x to the n is nx to the n minus 1. So you bring the power down, and then you subtract 1 from the power. 1/3 minus 1 is minus 2/3. Right? Remember our formula, our power rule, if you will. Con is asking if it's necessary to simplify completely. That's going to depend on the actual question. For now, not so much. But later on, simplification will play a huge role. What I want to go back to is this question before we move on, right? I mean, we decomposed it as the composition of two functions. We found its derivative. We're very clear with that. What are we going to do from now on if we're not decomposing it into a product, into a composition of simpler functions? We're going to ask the question, what do we have here? Here you have the cube root of something. So you differentiate the cube root. Derivative of cube root, 1/3, blah, 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 to the negative 2/3, right? Using the power rule, as Pamela pointed out. And then you differentiate the inside. Derivative of e to the x plus 1 is e to the x. That's what the chain rule says. Differentiate the outer function, leaving the inner function fixed, and then multiply by the derivative of the inner function. Of course, this chain rule can be proven using the limit definition of the derivative, right? So you can prove this in the same way that you can prove the product and quotient rules. All right. Now the question is asking us to just differentiate without necessarily decomposing it as a composition of simpler functions. Today is Monday, tomorrow is Tuesday. You have the regular tutorials, the Monday and Tuesday tutorials. Let's differentiate this. You have options, right? You could expand this, multiply this out 50 times. It is to the 50, correct? 50. But we're not going to do that. We're going to differentiate. And how would you describe this? You would describe this as a polynomial to the power 50. Something to the 50. So differentiate the something to the 50 using the power rule. The derivative is 50 blah 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 to the 50 minus 1 times the derivative of the inside. This is the inside. Derivative of x to the 5 is 5x to the 4. Derivative of 3x squared, 6x. Derivative of x is 1. There it is. Convinced? There it is. Should we distribute the 50? The answer is no. Factored is simpler. Factored is simpler. What happens if you have the product rule and chain rule in the same question? It happens. Absolutely. Take it one step at a time. Right? Look at this. First, let's rewrite this. Let's rewrite this as x squared minus 1 to some power. What's the power? You know what the power is. The power is minus 1/3. Thank you. And now let's differentiate. Right? What do we have here? We have something to the power negative 1/3. That's how you would describe it, right? So let's differentiate. Let's differentiate this. Let's differentiate the power using the power rule. Bring down the negative 1/3. Blah, blah, blah. To the negative 1/3 minus 1 or negative 4/3 times the derivative of the inside. That's the chain rule. times the 2x. Thank you. There it is. Paul is asking if we always need to bring the negative powers down. No, this would be acceptable. For now, at least. Keep in mind, again, though, right, that if you were given a multiple choice exam, which may happen on the final exam, some of the answers could be any way, any equivalent reformulation. So you have to be comfortable doing everything. What do we have here? How would you read this? You would say cosine squared. It's something squared. Pratik suggests a product rule, and you could write it as cosine times cosine, and that's very good. Nothing wrong with that. Absolutely. And then apply the product rule. But let's treat it as something squared. It's cosine squared. So we differentiate the square to cos, and then we differentiate the inside. Inside is cosine. Derivative of cosine is negative sine. There it is. Connor has decomposed it nicely as the composition of two simple functions whose derivatives you're familiar with. If you do it Pratik's way, viewing it as a product and differentiate using the product rule, you'll see that you get exactly the same answer. So it's nice to have a few ways to do it and to check your answer. It could also be viewed as negative sine 2 theta. Absolutely. Con is asking if cosine is a product. No, but I mean it's cosine squared, right? So this can be viewed as cosine theta times cosine theta. That's what Pratik was suggesting. We saw the derivative of e to the x was e to the x. So I suggested you take that as a rule for now, if you wanted to. Exactly that, Zia. Right? It's something squared, so we differentiated the square using the power rule. Absolutely. So we bring the 2 down and subtract 1 from 2. Alexis is asking, why didn't you plug in g of x for f of x for 14? I'm not sure what you mean here. I mean, let's not confuse. I mean, it's a terrible notation, right? Let's call it h so that we don't make any mistakes. But some people have decomposed it. Connor had decomposed this as f of x or f of theta was theta squared and g of theta as cosine of theta, right? So the derivative f prime is 2 theta and g prime is negative sine So write 2 theta, and where theta is replaced with cosine, so you get this part, and then that's g primed. This answer would be simple enough for now. We saw the derivative of e to the x was e to the x. My question to you is, what about other exponential functions now? What is the derivative of a to the x? For a bigger than 0, a not equal to 1. What, in other words, what is the derivative of an exponential function? Any exponential function. Well, you know that exponentials and logarithms are inverse functions of each other. So a to the x is the same as e to the ln a to the x. Right? Because exponentials and logarithms are inverse functions of each other. So these just cancel out. So instead of differentiating this, we could differentiate this. This, which by properties of the logarithm, this is e to the x ln a. So the derivative of this is going to be the same as the derivative of that. We can differentiate this instead, which may be simpler. What do we have here? Here we've got an exponential, e to the something. The derivative of e to the something is e to the something times the derivative of the inside. That's what the chain rule says. And the derivative of the inside, x ln a, derivative of x is 1. Ln a is just a constant. But e to the x ln a was a to the x to begin with. In other words, the derivative of a to the x is a to the x ln a. So let's write that down right here. Well, let's not. How did we differentiate ln of a to the x? Well, ln of a to the x is the same as x ln a. Why is it ln a? Well, it's x times a constant. X times 2. What's the derivative of 2x? You know it's 2. What's the derivative of 7x? Right? X times 7. X times ln a. The derivative is just ln a. Why wouldn't the derivative of a to the x be x to the, well, so cake, you're treating it as a power rule when it's not x to a number, but rather a number to the x. So it's an exponential, not a power rule. There's always asking why is it the derivative of e to the x ln a? Well, I mean, we have the work right here. A to the x is the same as e to the ln a to the x. Because exponentials and logarithms are inverse functions of each other, these just cancel out. Why do it? Well, this allows you to bring the x down And now you know the derivative of e to the x. So you can make use of that in figuring out what the derivative of a to the x actually is. The derivative of a to the x is a to the x ln a. Let's consider this example. What is the derivative of 5 to the root x? Well, this is 5 to the something. A to the something. The derivative is 5 to that something ln 5. Right? A to the x ln a, where a is 5, times the derivative of the inside, times the derivative of root x, which is 1 over 2 root x. Ben is asking, does it have to be ln, or can it be any log? It must be ln, because ln is the inverse of the exponential. Let's do a few more. Again, you're looking at this function now. How would you describe this? X times sine of pi x. X times sine of pi x. In other words, a product. Product rule applies. This is a product. So differentiate the first one, leaving the second one fixed. Plus, leave the first one fixed, differentiate the second one. What's the second one? Second one is sine of pi x, sine of something. Derivative of sine is cos. So cos of that something times the derivative of the inside. Chain rule kicks in. Derivative of pi x is pi. So you see it's a chain rule inside of a quotient rule, of a product rule. Very nice. All right, last one, and I'll let you guys go. Let's do 22 first, and then we'll go back to 16, and we'll decompose it as the composition of two simpler functions. Perhaps you should do that while we're working out 22. So first of all, how do we differentiate? How do you describe this? It's that times this. So it's a product. So somebody's asking chain then product, or is it the opposite? It depends. It depends on the question. you have to ask yourself, what am I looking at? What function am I working with? And here, what is that? It's this times that. So it's a product. Product rule. Differentiate the first one, leaving the second one fixed. But what is the first one? The first one is something squared. So to differentiate the first part, chain rule kicks in. You differentiate the square times the derivative of the inside. Derivative of the inside is easily seen to be -4, leaving the second one fixed. Plus, you leave the first one fixed, and you differentiate the second one. Well, what is the second one? Second one is the square root of something. So chain rule again. You differentiate the square root. 1/2 square root times the derivative of the inside. What's inside? X squared plus 1, whose derivative is 2x. How are we doing? Let's quickly revisit 16. For those who might not have gotten it. And I had suggested, should you try to expand and simplify? No. You might want to factor. The 2's cancel out nicely. You might want to factor a 1/root x squared plus 1 from the whole thing, and one of these. That sounds pretty good. So what am I saying? If you wanted to simplify this, I would factor out a 1 minus 4x over the square root. And get some stuff in here. I was suggesting here that you should decompose this as the composition of two simpler functions. What functions am I referring to? Functions whose derivatives you're comfortable with. F of x is 5 to the x. G of x is square root of x. So that if you look at the composition, g is root x, and everywhere you see an x in your function f, you replace with root x. And if f is this and g is that, what is g prime? You know what g prime is, right? It's 1/2 root x. Right, this is x to the 1/2. So the derivative is 1/2 x to the negative 1/2. Absolutely. And 22, we were, when differentiating each of these parts in the product rule, the chain rule kicked in. So g prime is this, and f prime, well, this is a to the x. So the derivative is a to the x ln a. And now let's put everything together. dy dx, according to the chain rule, is f prime of g times g prime of x. G is root x, so that's f prime of root x. And g prime G prime is 1 over 2 root x. Everywhere you see an x in your f prime, you replace with root x. So we get 5 root x ln 5 times this, or let's put it over 2 root x. Exactly the answer we had here. How are we doing here? Questions? All right, so I'll have office hours tomorrow if you want to see me. Otherwise, you guys have a good weekend, and I will see you on Monday. You guys take care.